Hello guys, and the topic of our concern in this video is about projectile motion. My name is Dr. Garuma Abdisa. Let us see a projectile motion on this coordinate system, on the XY coordinate system. Let us first observe the trajectory of this ball. The path of the projectile is called the trajectory of the projectile. And the x component of the velocity, that is the initial velocity u, is u cosine of theta, and the y component of the velocity is u sine of theta. Let's modify these two kinematic equations for a projectile motion. Since we have started talking about kinematics, that is about study of motion, the final velocity is initial plus at, and the displacement is initial velocity times t plus a half at squared, are part of the very fundamental kinematic equations that we are going to make a modification so that it will turn out to be appropriate for the projectile motion. So the component of the velocity is final velocity is u plus at, and then we are going to be based on this very general kinematic equation, and we will modify it in terms of the x and y components for a projectile motion. And this is the way we will go ahead. Because projectile motion is a kind of two-dimensional motion, Vx is equal to ux plus ax times t based on this kinematic equation. The same applies for the y components of the motion. And because ux is u cosine of theta and the y component is u sine of theta, and ax is equal to 0 because there is no gravitational acceleration along x, but ay is equal to minus g. Therefore, in this case, Vx simply becomes this ux part, which is u cosine of theta, because this term will vanish because ax is equal to 0. And in this case, Vy is equal to u times sine of theta, which is this uy, u sine of theta. Ayt becomes minus gt because ay is minus of gt. So these are the x and the y components of the velocity of the projectile motion. Notice that the x component of the velocity has no time dependence, while the y component has time dependence associated with it. There is no t with this equation, means it doesn't depend on time. But here we have the t term here, means the y component depends on time. Let us see that with this demonstration. As the ball arrives at here, these are the x component of the velocity, and that is the y component of the velocity. So as the ball arrives at this point, this is the x component, and this is the y component of the velocity. And you have to observe that the x component has always the same direction and the same magnitude, but the y component of the velocity at one time may be a little shorter. It's here, Vy is u sine of theta minus gt. Sometime later, now it is up. Sometime later, it will also be down, but it could be even longer in magnitude, larger in magnitude. So the y component changes itself with time, but the x component is always a constant. Also at this point, as you can notice, the x component has still the same direction and the same magnitude, but the magnitude of the y component is now increasing because this arrow is larger than this one. It shows that the y component of the velocity is changing both magnitude and the direction with time. The size and the direction of Vy changes, but the size and direction of Vx is the same throughout the motion. This is something very important, and you have to pay attention to it. Now we will make some modifications based on this general kinematic equation. Displacement is ut plus a half at squared. These are the x components. Sx is uxt plus half ax times t squared. That is based on this one. You have to always remember that whenever we take the general kinematic equation and we want to modify that to a projectile motion, we have to always consider component-wise. And for the y component, the same. So ux is simply u cosine theta, uy is u sine theta, ax is again 0, no gravitational acceleration along x, but ay is minus g for the y direction. And let's call the x component of the displacement to be x and the y component of the displacement to be y. So simply x that is this Sx is simply x for simplicity, that is ux times t, so u cosine theta times t, very straightforward. Likewise for y, that is uy times t, that is uy u sine theta times t minus a half times ay, that is minus gt squared. So x is u cos theta t, y is u sine theta times t minus a half gt squared. Let us see that with some simulations. This is the projectile motion. Whenever the projectile is here, that is my height y, and this is the position x. Simply y and the x's are shown here. Whenever my projectile is here, that is my y, and this is my x. The general formula for y's and the x's are here. And notice that the vertical and horizontal positions of the projectile at every time is given by x is u cosine of theta times t, and y is u sine of theta times t minus a half gt squared. Now let us see the maximum height of a projectile. Whenever a projectile goes on like this, what happens is, this is the maximum height. At the maximum height, vy, that is the y component of the velocity, becomes 0, but vx is always u cosine of theta. So this is vx and this is vy. Carefully notice what happens. This is once again vx and vy. This is vx and vy. Observe that the magnitude of vy is decreasing. Vy is larger here, is becoming decreasing until it eventually becomes vy is equal to 0 on the top. These are vx and vy. And here, vx and vy. Vy is now starting by changing the direction to be downward. Now, in the sense of downward, vy is increasing its magnitude, but vx is throughout the motion the same. As you can now observe, vy is increasing as it moves downward, as it was decreasing from this side. Here is vx and vy. So as we observe, at the maximum height, vy is equal to u sine of theta minus gt, that is the y component of velocity, becomes 0 on the peak. This is very remarkable for us to achieve the maximum height, because from vy is equal to u sine theta minus gt is equal to 0. This is the time to arrive at the maximum height, which is t, I will call that time to be t up, is equal to u sine of theta over g. At the maximum height, that is at this given t up time, y is equal to sine theta times t minus half gt squared is a general formula for every height at every time. So y max is equal to u sine theta times t up, that is the time taken to arrive at the top, minus half g times t up the whole squared. So if we directly substitute t up in this y max formula, and with some little algebraic manipulations, we arrive at y max is equal to u sine squared theta over g minus a half u squared sine squared theta over g. And then finally, y max is equal to u squared sine squared theta divided by 2g. So here is some visualization of the maximum height. This is our projectile. And whenever the projectile is here, that is what we call at the maximum height. That height is given to be u squared sine square of theta divided by 2g. The maximum height occurs at the peak, that is at the turning point of the motion. At this peak point, vy is equal to 0 and y max is equal to u squared sine squared theta divided by 2g is the general formula for the y max. Now let us move on to the range of a projectile. If this is our projectile motion, this is what we call it the range of the projectile. That is the position it will arrive on the same level as it started with. So these are correspondingly the heights. As you can see, the height is up to the maximum height is increasing, and finally here it decreases. So in this interval, y increases up to the peak, and from the peak down to the ground, the heights decrease. So finally, at this, whenever the ball is back to the same level as it started with, The general formula for y is u sine of theta times t total, that is the total time, because now every time is completed and the ball is now back, minus half g t total is the whole squared, becomes 0. So this time here is t total. At this t total, now the object is back to the same level, and from this we can find the total time. So this is what I wrote. So the total time is straightforward. It is simply 2u sine of theta divided by g. Previously we proved out that t up, that is the time from the initial to the peak point, is u sine of theta divided by g. We found that already. And we can compare these two equations in that is the t total and the t up. That t total is simply twice of t up. From this we can deduce that time to move up is equal to time to come down to the same level. Time to ascend to the top is equal to time to descend from the top down to the same level. So let us visualize that. If this is our projectile, then time from here to there is called t up, which is u sine of theta divided by g, and the time from there to here, which is called t down, is also u sine of theta divided by g, and the overall time, that is t total, is equal to t up plus t down, that is the total time, is simply twice of u times sine of theta divided by g. Carefully notice the relationship between t total, t up, and t down. Now the range is straightforward once we find the t total, because we simply place range to be u cosine of theta times t total, but the t total is given to be 2u sine of theta over g. With direct substitution, we get the range to be u squared times sine of twice theta over g. Remember that sine of twice theta is simply sine of theta plus theta, which is 2 sine theta times cosine of theta. When we reduce this equation back to this one, we will make use of this one.